Good morning everyone. So welcome to my YouTube channel Math Circle. So today we are going to see 11th lecture on infinite series. Today we will study what are the alternating series and what are the conditionally convergent series. What is alternating series? A series having a series having terms positive and negative alternatively is called an alternating series. For example, I am taking this. I am taking this 1 minus 1 upon 2 plus 1 upon 3 minus 1 upon 4, and this is going like this. Okay. So how we can write this series? So this is alternative. First term is positive, second term is negative, third term is positive, fourth term is negative. Okay. So how to write this series? So we can write this series as in the following form: 1 plus 1 minus, so put u n is equal to un is equal to 1 upon n. The series can be written as, how we can write this? The series can be written in this form: summation n goes to 1 to infinity minus 1 to the power n plus 1 un. We have un is equal to 1 by n, that is greater than. Okay. Now example 2. You see this one: minus 1 plus 2 minus 3 plus 4 minus 5. Okay. So this series, to put, this is also alternating series: minus 1, minus, its first term is minus 1, then positive term 2, and third term is negative, fourth term is positive. So I'm taking un is equal to n. Then the series can be written as summation n goes to 1 to infinity minus 1 to the power n un, where un is equal to n, that is greater than 0. Okay. So I am writing a result. You can say proposition, or I am calling it a note. Let summation n goes to 1 to infinity a n be an alternating series, then summation n goes to 1 to infinity a n is equal to, either this can be written in this form or where un is equal to, okay. So we have taken two examples and we found that un is positive. And actually here you see in example 1, un is nothing but, you see that un is an. What is an here? An is here. What is an here? An is minus 1 to the power n plus 1 upon n. So you see that un is my this, and an is nothing but 1 upon n, that is un. Okay. And here also you observe that, okay, in second example you also observe that what is an? An is minus 1 to the power n, n. So an is 1, that is un. Okay. So we have this one. So that is why I have written this. Alternating series, either first term will be positive or first term, or maybe it can be negative. Okay. If first term is positive, we can write like that. If first term is negative, we can write like that. Okay. So now Leibniz test. Let summation n goes to 1 to infinity minus un be an alternative series okay, where un is positive for all n comes to n. Okay. Then the series is convergent if the following conditions are satisfied. Satisfied. First, un is a monotonically decreasing sequence. It means what? Un plus 1 is less than un for all n belongs to n. Second, limit of un, limit of this sequence is nothing but 0. Okay. If you have a alternating series and un is such that un is monotonically decreasing at its limit and tending to infinity is 0, then the series is convergent. Okay. So let's see its proof, how it will work. Okay. So now we consider this summation Sn is equal to, what is Sm here? What is Sk here? Sk is nothing but summation n goes to 1 to is a minus 1 to the power n plus 1 un. Then S to m is equal to summation to m plus 1 u, sorry, n plus 1 un. Okay. Now, how we can write this? How we can write this? uh, so, so what is S to m plus 1? That is S to m plus 2. That is nothing but we can write n goes to 1 to m minus 1 to the power n plus 1 un, and that is this is S to m here. Okay. So this is to m. So S to m is equal, S to m is n goes to 1 to 2m summation this, and what will be S to m plus 1? That is to S to m plus 2. That is this, and we can write next two term S to m plus 1 minus u to m plus 2. And this is nothing but S to m. Okay. So this implies S to m plus 1 minus S to m is equal to u to m plus 1 minus u to m plus 2. But since this sequence, so actually I have written like that. Sequence is written by this way. I am writing the changing the thing. Sequence is written by this way. Now since this sequence un is monotonically decreasing, we get u 2m plus 2 is less than u 2m plus 1. It means u 2m plus 1 minus u 2m plus 2 that is greater than equal to 0. So this implies s 2m so this implies s 2m plus 1 minus s 2m is equal to u 2m plus 1 minus u 2m plus 2. That is all. We have this one. So s 2m is less than s 2m plus 1. So rule m belongs to m. Okay. So this sequence is monotonically increasing sequence. Okay. Next, what is s? Next, Sn is actually sk is always equal to, this is equal to summation n goes to 1 to infinity minus 1 to the power n plus 1. That is k. So this is nothing but u1 minus u2 minus u3 minus u4 minus u5. Okay. So this is going like that. Last term is un minus 1 minus un. Okay. Okay. Now as 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 u2 minus u3 is non-negative, u4 minus u5 is also non-negative. So we have these terms, the difference of these terms is non-negative. We have sk is less than u1. Okay. Sk is less than u1 for all k belongs to n. So therefore, so this implies implies S2M is also less than U1 for all M belongs to. So this implies this sequence is bounded above by U1. It means U1 is an upper bound for S2. Okay. Now this sequence is monotonically increasing and bounded above. So this implies S2M is monotone and bounded. Therefore, by monotone convergence theorem, this sequence is convergent. Okay. Let's say because this sequence is convergent, let's say limit m tending to infinity S2M is L. Okay. Now consider S as now if this sequence is tending to L, we also have so limit m tending to infinity S2M is equal to L also implies if it because it is a even sequence is convergent, it's limited. If we take in place of m we are taking m minus 1, the limit will be same. Okay. Now we consider this sequence. Consider the odd sum S2M minus 1. So that is nothing but S2M minus 2, and it can be last term can be added as Q 2M minus 1. Okay. Now limit m tending to infinity S2M minus 1 is equal to limit m tending to infinity S2M minus 2. Okay. So that can be written as S2M minus 1 plus U2M minus 1. Okay. Okay. So this is L and this is 0. This is 0. This is 0 and this is L. Okay. Because limit n tending to infinity un is 0. This implies limit m tending to infinity u to m minus 1 is also 0. Okay. Okay. So this implies S to m is also convergent and converging and limit m tending to infinity S to m minus 1 is also L. Okay. Now S to m converging to L and S to m minus 1 sequence is also converging to L. So this implies main sequence Sk converging to L. Okay. So this implies this series is converging to L. It means this series is convergent. Okay. So this theorem is proved now. Now one thing you observe that note. So let this series be an alternating series. Then what we will do, we can write this series un in this form minus, okay, we can write like this. So therefore, so this, so we have, so now this series is convergent, if and only if this series is convergent. Convergent. Okay, this series is convergent. So what we conclude, we conclude that Leibniz test can also be used for the alternating series of the form we have. So we have proved Leibniz theorem for certain alternating series in which first term is positive. But Leibniz rule can also be used for alternating series having first term negative. Okay. So we have mentioned why it is working. So it is working like that. Because a alternating series with first term negative can be written as a negative time of this series, alternating series having first term positive. So by Leibniz rule, we can conclude the convergence. Okay, if it follow all the rules of Leibniz test. Okay. Now we are going to go ahead. So what is example? Example. Example. You see this. This is a summation n goes to 1 to infinity minus 1 to the power n plus 1. It means 1 upon 2 plus 1 upon 3 minus 1 upon 4, like that. Okay. Now what is un here? Un is 1 upon n. Okay. Note that this sequence un, that is the sequence, is monotonically decreasing. We know that monotonically decreasing. Second, what is the limit of un is equal to? Okay. So this series is alternating series. This is alternating series. This is alternating series which satisfy all the conditions of Leibniz test. Because in Leibniz test, un should be monotonically decreasing. It is happening in my case also. And limit of un should be 0. That is also by Leibniz test. By Leibniz test, the series is convergent. Okay. Now example 4. Consider the series summation n goes to 1 to infinity minus n to the power n plus 1, 1 upon n to the power p, where p is greater than 0. Now see this series. So what is un here? Un is 1 upon n to the power p. Okay. Now what is we know that this sequence is also monotonically decreasing. Power is positive. As you will increase n, it will decrease. So note that this sequence is monotonically decreasing. Taking limit n tending to infinity. Un is equal to limit n tending to infinity 1 upon n to the power p is 0. Okay. So it satisfies all the condition of Leibniz test. By Leibniz test, thus the series summation n goes to 1 to infinity minus 1 to the power n plus 1 upon n is convergent. Okay. So this is done. Now we start next topic, conditionally convergent series. If series summation n goes to 1 to infinity an if series is summation n goes to 1 to n is said to be conditionally convergent if this series is convergent but its absolute value series is divergent. Okay. A series is said to be conditionally convergent if this series is convergent but its absolute value series is divergent. Okay. It means not convergent. In other words, a conditionally convergent series is a convergent series which is not absolutely convergent, which is not absolutely convergent. A conditionally convergent series is a convergent series which is not absolutely convergent series. Okay. Okay. So this is not absolutely convergent. So example, see this series summation that is 1 minus 2 plus 1.3. Okay. So we have already checked that this series is convergent. By Leibniz test, we have already checked that this series is convergent series. Okay. But now, whether it is absolutely convergent, let's check. So what is its absolute value series? You add mod word, mod. So what is this? But here n to the power p. This is divergent. And power of n is 1 upon n to the power p. If p is 1, that is 1 upon n. This series is divergent. We already know. Okay. So we have this series minus 1 to the power n plus 1 upon n. That is convergent but not absolutely convergent. Okay, since this series minus 1 to the power is convergent, convergent, but it is not absolutely convergent. Therefore, summation n goes to 1 to infinity minus 1 to the power n plus 1 is conditionally convergent series. Okay, conditionally convergent series. Now another example, this series. That is 1 minus 1 upon root 4. Okay, by Leibniz test, because this is alternative series, by Leibniz test, we can check this series is convergent. Because what is un? 1 upon n, 1 upon under root, that is monotonic reducible, and limit of un is tending to 0. So this series is convergent by Leibniz test. Okay. Now what about its absolute series? So what is p-value here? P-value is 1 over 2. That is less than 1. So this implies this series, that is this series. In auxiliary series, if value of p is less than 1, the series is divergent. Okay. So this series is divergent. Okay. Since this series is convergent but not absolutely convergent, absolutely convergent, we get this series is conditionally convergent. So note that a conditionally a. So I am writing in next line. Note that conditionally a conditionally conditionally convergent series is also called semi convergent. Convergent series. Okay. A conditionally convergent series also known as semi-convergent series. Okay. In some books you find semi-convergent series is written in place of conditionally convergent. Okay. So today's lecture up to this, if you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much. We will see you for next lecture.